All right. It's 9:03. Let's get started. So some limit type things you're probably going to see when you use the definition of the integral or the area of the curve. And they're not too terrible. This limit, no one is expecting you to show any work here. The idea is that since we know that n is going to infinity and the highest power of n on the top and the bottom is 3, the limit's just going to be the quotient of those leading coefficients. And that's all the work anyone is expecting to see. You could do more work, but you don't need to do more work. Same deal down here. This one's going to turn out the same. There is a little bit more internal work we have to do, but no one wants to see your work here. What I really want to see is that I know that if I multiply out the top, I'm going to have an n to the fourth. It's going to be 2n times 4n times 3n squared, which is going to give me a 12n to the fourth over a 5n to the fourth. So this limit's going to be 12/5. And that's because if I were to multiply this out, I would have the limit as n goes to infinity of, on top I'd have 12n to the fourth plus terms I don't care about, right? Something n cubed, something n squared, something n, and a constant, but I'm not going to find those. On the bottom, I still have 5n to the fourth plus 3n cubed plus 2n squared plus 6n plus 1. I mean, you really could multiply at the top if you wanted to, but that's not really the point. But just to show the work here, if you're to multiply this out, this part would be, let's see, 4n times 3n squared is 12n squared. Oh, I missed it. So you guys might be like, why is he making a mistake here? Because I made a mistake, right? What's the actual number I should have on top? Not 12, because I missed what? I missed the 2, right? That should be a 2 times 12 over 5. I should have a 24. That's why it's good to check your work. N to the fourth. But if I multiply this out on top, so sometimes multiplying that's worthwhile. So I have a 12n cubed plus a 3n squared plus an 8n plus a 2. And if I distribute the 2n to each of those, I get 24n to the fourth plus a 6n cubed plus a 16n squared plus 4n. But again, when we actually find this limit, these terms that have the same highest powers are the only ones that actually matter. So the limit ends up being 24/5, not 12/5, 24/5. Yeah.
So they have the same like power, like in bottom left n to the fourth. Like what if the top one was n to the fourth and the bottom one was n to the fifth?
Then the limit would be 0. If the power on top is lesser, then the limit's be. But I'm going to tell you that when you're doing these limit definition of the integral problems, that's never going to happen. You're always going to have the same highest power on top and on bottom when we're doing those types of problems. It just always ends up working out that way. Which brings us to actually, yeah, is that where we're so there's a couple different ways to go here. Let's go ahead and do a limit definition of the integral problem. Here's one that's similar to problem number 18 from section 5.1. This is 5.1, number 18 with a twist. We want to do the, oh, sorry, not 18, apologies. Yeah, no, 18, that's right. Sorry. So we want to use the limit definition of the integral to find the integral from 0 to 1 of x to the fourth dx, not x to the third, which is what the problem actually has. And we're going to be given a formula here. We're given that 1 to the fourth plus 2 to the fourth plus 3 to the fourth plus all the way to n to the fourth, which one could write as the sum from k equals 1 to n of k to the fourth. That's going to be equal to a formula you definitely do not have to memorize. N times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1 all over 30. Not a formula you need to memorize. I had to look it up. So we're going to start by doing the usual things. If I want to find or express the integral from 0 to 1 of x to the fourth dx as a limit, it's going to be the limit as n goes to infinity of the sum from k equals 1 to n. And right here is where we have to write two things. We need our f of x sub I and our delta x. That's always what's going to go in this summation when you're finding the limit definition of the integral. The function f of x is just what's in the integral. It's also called the integrand. There's your f of x is x to the fourth. To find x sub I, we first need delta x. So here our delta x is just the width of each subinterval. I like to draw a picture here. I like to think of like I'm actually taking the interval from 0 to 1 and breaking it up into n little subintervals, but you don't need to draw this picture. If you remember the formula, the delta x is just b minus a divided by n. That's going to be a 1 minus 0 over n. It's just 1 over n. Perfectly fine to memorize that. Also, x sub I. You could draw this little picture here like I'm doing and say, oh, here's my first x, it's x sub 0, and then there's x sub 1, x sub 2, et cetera, et cetera, et cetera, all the way to some x sub I minus 1 and some x sub I. And we can see that each of these is delta x apart. So x sub 1 is just delta x, which is 1 over n. X sub 2 is a delta x plus another delta x. So it's going to be 2 times delta x, which is 2 times 1 over n. And if you keep going this way, x sub 3 is 3 delta x, which is 3 times 1 over n. You're eventually going to get down to saying that x sub I is I times delta x, which is I times 1 over n. Or I over n, as I would probably
Paper up,
choose.
please.
Go ahead.
Can
Yeah.
you move your
Oh,
paper
yeah.
up, please?
K. Sorry. So sometimes we use K, sometimes we use I. I started using K and then I switched over to I accidentally. Yeah. So I guess right here I should have been more specific. I guess I'll go with I since I wrote I's here. So I'm going to go from I equals 1 to n instead of K equals 1 to n. Pretty interchangeable. You might want to see what I'm writing at the bottom there. Sorry about that. Or you can just remember that x sub I is always going to be a plus I times delta x, which in this case is going to be 0 plus I times 1 over n, which is I over n. And then we're going to substitute that into our function. So f of x is x to the fourth. F of x sub I is going to be f of I over n, which is just going to be I to the fourth over n to the fourth. Okay, so now in our formula here, our f of x sub I is going to be I to the fourth over n to the fourth. And our delta x is going to be 1 over n. And that's what we're trying to figure out the sum of. Questions about any of this? Okay, the rest of it's not too terrible since they've given us a formula. So here's what we're going to write. And let's give ourselves some more room here. So taking this limit, I'm going to cover up this bottom part for a second. This limit as n goes to infinity of the sum from I equals 1 to n of I to the fourth over n to the fourth times 1 over n, I would rewrite as the limit as n goes to infinity of the sum from I equals 1 to n of I to the fourth over n to the fifth. And I'd be like, oh yeah, I'm where I want to be. My power of n is 1 larger than my power of I or k. That's always what we want to see happen. Then things are going to work out. We're going to pull out the constants, and in this summation, n is considered a constant. We want the formula that we have to show us. So here I'm going to say, great, I have the limit, n goes to infinity, of 1 over n to the fifth times the sum from I equals 1 to n of I to the fourth. But that's exactly the same as that. I'm just using I instead of k. So that thing I've circled is really equal to n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1 all over 30. So that's what we're going to get. We're going to get the limit as n goes to infinity of 1 over n to the fifth times n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1 all over 30. We don't want to multiply that out, but we do want to be more careful than it was the first time I did. So being extra careful here, I see that on top, if I did multiply it out, I would have an n times 2n times 3n squared, which is going to be 3 times 2 is 6. It's going to be a 6n to the 5th plus lesser powers of n that we don't care about. On the bottom, I have a 30 times n to the 5th. So then the limit of this is going to be exactly 6 over 30, which reduces to 1/5. And it is correct to say that the integral from 0 to 1 of x to the 4th dx is in fact is in fact 1/5. I was trying to do the intermediate fundamental theorem calculus part, which is not quite there, but we're going to talk about it a little bit later. So that's how you can do a problem like that. There was something else here as well. Oh yeah, being more general about writing integrals as summations. If, for example, we were told to express the area under f of x equal to x squared times sine of x, where x is between 0 and pi, as a limit, well, here's what we're going to do. I'm going to write it as an integral first, just because it feels easier to write it as an integral. So if I was writing this as an integral, I'd say, well, it's going to be the integral from 0 to pi of x squared times sine of x dx. And all that means, oh, sorry, I don't know why that froze up there. That's interesting. Okay, it's weird, but it fixed itself. So this just means the area under the curve. Area under f of x equal to x squared sine of x between 0 and pi. If we want to write this as a limit, I'm starting at the same place I started before. I'm going to write the limit of the sum of, and I'll use k this time, the sum from k equals 1 to n. This part here is the same as before. It's going to be your f of x sub I, and we're going to multiply that by our delta x. Here, our delta x is going to be pi minus 0 divided by n, or just pi over n. Our f of x sub I, we're taking our function x squared times sine of x and replacing each x with whatever x sub I happens to be equal to. Using the formula for x sub I is a plus I times delta x. So in this case, that's going to be 0 plus I times pi over n. Or pi I over n, as I would probably choose to write it. So instead of writing x squared times sine of x, I'm going to write pi I over n quantity squared times sine of pi I over n. And that's all we can, well, that's all we're being asked to do here, and that's all we can do here. There's nothing more we can do to simplify this other than like squaring this out and multiplying things together, but there's no value there. That's how we express an area under a curve as a limit definition of an integral without actually doing anything else. All right. I'm going to keep going. Obviously, you're welcome to stop me and ask questions. I'm going to try my best not to say, do you have any questions? Because if you have questions, you can just ask them. Do you have any questions? Sorry, can't help it. Yeah. We will probably cover some of 5.2, which is what? The fundamental theorem of calculus? Yeah. Yes, I was just, so the reflections, there were a lot of questions about things that happened last week. So I was trying to cover a few things, but yes, we're definitely going to get to the fundamental theorem of calculus. It's on the agenda. There's a few questions from Diddel's discussion sheet, which I thought were worth looking at. So let's take a quick look at the following. So one of the questions was, and also I should point out before we do any of these, I should just mention, which is why we're not going to cover all of them, that if you're in Diddel's class and you look at Canvas, which is what, right there, there's Diddell, yeah. I will point out that he does post, can you see this? No, you cannot. Why not? Let's do that. you can see that he does post the solutions to the discussion sheet. So not that I'm not happy to go over things, because I know solutions aren't always 100% clear when they're written necessarily, but just so everyone's aware, the solutions are there to look at as well after the fact. Anyway, let's look at a couple problems here, specifically problem 2A and B. The 2A was given y equal to e to the tangent of 3x. He wanted you to find the derivative dy dx. And so what we're really being asked to do here is just use the chain rule. I have e to the stuff. Here's what I'm always thinking. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff, but I said the magic word stuff, so I have to multiply by the derivative of the stuff. Or in other words, I have to use the chain rule. So the derivative of e to the tangent of 3x is going to be e to the tangent of 3x, and then I have to multiply by the derivative of tangent of 3x, which is going to be e to the tangent of 3x times the derivative of tangent of some new stuff is secant squared of that stuff multiplied by the derivative of the inside stuff. So there's the derivative of e to the tangent of 3x. It's e to the tangent of 3x times secant squared of 3x times 3. And the reason we really ask this question is because then the next question is asking you to kind of undo it for a slightly different function. So 2b, we're being given that f of x is equal to secant squared of 5x times e to the tangent of 5x, which looks almost exactly like this, except we have 5x instead of 3x. Question?
When you did the chain rule, where did the times 3 at the very end?
So when I took the derivative of tangent of 3x, I had to use the chain rule again. So I am thinking of this as tangent of some new stuff, and the derivative of tangent of some new stuff is secant squared of that new stuff, but then I have to again multiply by the derivative of the new stuff, which is the derivative of 3x is 3. So here, if I want to find the antiderivative, well, I can see from the previous problem that the derivative of e to the tangent of 3x is essentially e to the tangent of 3x times secant squared of 3x, and then there's the constant here, which I'm going to figure out later. So if I'm trying to find a function whose derivative is e to the tangent of 5x times secant squared of 5x, it looks like e to the tangent of 5x is a pretty good guess. It's not right, and we're going to fix it. But let's check. If I take the derivative here, the derivative of e to the tangent of 5x is going to be e to the stuff times the derivative of that stuff, but then the derivative of tangent of 5x is secant squared of 5x times 5. And you might notice this original function is missing that times 5. So to adjust for that, we're going to divide by 5 or multiply by 1/5. And now it works. Now the derivative of 1/5 times e to the tangent of 5x is 1/5 times e to the tangent of 5x times secant squared of 5x times 5, which just simplifies down to e to the tangent of 5x times secant squared of 5x, which is exactly the same as that, as it should be. So here is our antiderivative. Oh, what I forget? The plus c. Cool. So I'll point out that a lot of questions on this first discussion sheet that he gave you all were first asking you to find the derivative and then kind of giving you a function very similar to the derivative you just found to anti-differentiate, kind of help you see what the pattern might be. In the same sort of way, let's look at problem 3 here. Because problem 3 has some chain rule stuff that I think we should look at. Try to keep things in order here. Kind of. So here's problem 3A. They want us to find some derivatives, specifically given y equal to sine squared of 3x, and also y equal to sine to the 5th of 3x. We want to find some derivatives. So I don't love writing sine to a power like this, specifically when we're finding the derivative of it. It's just a little bit unclear what my outermost function might be. So I would encourage you all, if you have to take the derivative of a trig function to a power, to rewrite it as sine of 3x quantity squared. Or over here, sine of 3x quantity to the 5th. Because then it's clear to me that the outermost function is something being squared. I know the derivative of x squared is 2x. Oh, sorry, there's a question. Why is a 0? I'm not sure where sorry. So again, for those of you in the chat, if I'm not answering your question, it's probably because I'm just not looking over there. I'm not sure what your zeros are referring to, Meredy, so you're welcome to clarify.
It was when you said that it's a plus I plus the delta x, and I was asking why a is 0.
Sure. So for that problem, that's a good question. I'm definitely happy to clarify that. And it'll only take a second here if I can just get back to the page. The reason it was 0 is because that was your lower limit of integration. So when you have an integral like this from 0 to 1 of x to the 4th dx, that lower limit of integration is called a. That upper limit of integration is typically referred to as b. That's what's going on.
Oh, okay, thank you. I remember now.
So back here, the derivative of something squared is going to be 2 times that something to the first power, which we're not going to write, multiplied by the derivative of the inside stuff. And the derivative of sine of 3x is cosine of 3x times 3. Similarly over here, let's just draw like a little line down the middle here. dy dx over here is going to be 5 times our stuff to the 4th power. And then again, we have to multiply by the derivative of the inside, which is the same as over here. It's going to be cosine of 3x times 3. All of this to help us set up the question. If we're given that, so here's part B. If we're given that your function f of x is equal to 15 times cosine of 5x times sine of 5x, what's the antiderivative? Well, I know the derivative of sine squared of something is essentially going to give me sine of that something times cosine of that something. I'm trying to find the antiderivative of sine of something times cosine of the same something. So it's probably going to be something like sine squared of 5x in this case. Let's figure out what it is. So here's my guess. My guess is just that it's going to be sine squared of 5x. I know that's not going to be right. I know I'm plus c. Okay, plus c. I know it's not going to be right because I know the constant's just going to be off. We could try to fix it before we actually write out the problem. So let's see. If we end up taking the derivative here, we know we're going to get 2. What other constant is also going to be a factor here? 5. So we're going to get 2 times 5, which is 10. But we want the derivative to be 15. So we need to multiply that 10 by 15 over 10 to get 15, which you could reduce to 3/2 if you really wanted to. So I'm pretty confident that we're going to need a 15 over 10 out in front. Well, let's figure it out. So if I take the derivative here, my f prime of x is going to be 15 over 10, which I know is 3/2, times the derivative of sine of something squared, which is sine of 5x squared, is going to be 2 times sine of 5x times the derivative of sine of 5x, which is cosine of 5x times 5. And yeah, that works. The 2 times 5 is 10, and that cancels with the 10 down here, which gives me 15 times sine of 5x times cosine of 5x. Cool. Worked out. The other one, part C here, asks us to find, where'd it go? Sorry. Okay, it's giving us that our function that we want to find the antiderivative of is going to be 15 cosine of 5x times sine squared of 5x. Now that's a little trickier because neither of these functions have a derivative that gives me a sine squared, but they're asking us to look for a deeper pattern. So I can observe that when I took the derivative of sine squared, I got sine to the first times cosine. And when I took the derivative of sine to the fifth, I got sine to the fourth times cosine. So if I want to end up with sine squared times cosine, I probably need to start with sine to what power? Yeah, to the third. So my guess is going to be that my antiderivative is going to be sine cubed of 5x plus c. And I'm not even going to try to figure out what the constant is right now. I'm just going to take the derivative and see what I get. It might actually end up being what I want, which I didn't realize until just now. But let's take the derivative and we're going to get, let's see. And let's be smart about this. Let's write this as sine of 5x quantity cubed, so it's easier to differentiate. My derivative is going to be 3 times my stuff to the second power times the derivative of that inside stuff, which is cosine of your new stuff times the derivative of your new stuff. And yeah, that exactly works out to be 15 cosine of 5x times sine squared of 5x. So this is the correct antiderivative. We didn't need to adjust because we happen to be lucky. What Dr. Nadell and probably the other professor is trying to lead you up to is to get used to seeing this kind of thing, because what we're really doing is we're just employing U substitution without actually saying we're doing it. But really, when we start talking more in depth about antiderivatives, U substitution is one of the most frequent methods you will use to anti-differentiate things, which is why we are trying to show you all these things that happen when you do it without actually saying we're doing it. And to that end, let's look at one more problem on this discussion sheet, which is problem 4, and we'll not look at the entirety of problem 4, but just part of it. So problem 4 starts with this: given that y is equal to the natural log of x cubed plus 3x plus 6, find dy dx. So as a reminder, the derivative of the natural log of x is 1 over x. So the derivative of the natural log of some stuff is going to be 1 over all the stuff. And then what are we going to multiply by? Always, if I've said the magic word stuff, I'm going to say the derivative of the stuff. So in this case, the derivative of the stuff is going to be 3x squared plus 3. And I happen to like writing it off to the side like this, but it's probably going to be more convenient to write it as a single fraction, 3x squared plus 3 over x cubed plus 3x plus 6. And more generally, the rule that we're kind of trying to actually show here is that if your function is, say, the natural log of just some f of x, then your derivative is going to be 1 over f of x times the derivative of f of x, which becomes f prime of x over f of x. Which means if you see a function that you want to anti-differentiate that looks like a derivative on top of a function, its antiderivative should end up being the natural log of that bottom function. So for example, if we're given, say, and this is problem A, if we're given that our function is x cubed plus 4x divided by x to the 4th plus 8x squared plus 16. So let me ask you, is the top the derivative of the bottom? Is it exactly the derivative of the bottom? No, it's not. Is it close enough? Let's see. If I actually take the derivative of x to the 4th plus 8x squared plus 16, I end up getting 4x cubed plus 16x. And if I factor out that 4, I get 4 times x cubed plus 4x. So I'm close enough that I can make it work. If I'm off by a constant multiple, I can almost always fix that. So what I'm going to do here is I'm going to say, well, I think my antiderivative should be something like the natural log of x to the 4th plus 8x squared plus 16. But we know that if we take the derivative of this, we're going to get 1 over all of that times 4x cubed plus 16x. But I don't want that extra factor of 4, so I'm going to have a 1/4 out in front to account for that. We can check. If I take the derivative, it's going to be 1/4 times 1 over my stuff times the derivative of the stuff, which I'll put in the numerator, and the derivative of x to the 4th plus 8x squared plus 16 is 4x cubed plus 16x. But then I can factor out a 4 from the top, and it'll cancel the 4 down there, and I'll get 1/4 times 4 times x cubed plus 4x over x to the fourth plus 8x squared plus 16. And those fours cancel, which is exactly what it should be. Yeah.
So I'm a little confused on how you, so you're given a function, you're taking the derivative of the top and bottom.
Not exactly. So what I'm really doing is, so if I'm trying to use this specific version of the rule, I'm taking the derivative of the bottom and hoping it's exactly the same as the top. And here I was off by a constant, so I tried to fix that. But if on the other hand, say someone gave us, I'm just going to make something up now. If someone gave us g of x equal to, sure, let's start off at the bottom, James, x cubed plus cosine of x, and the top was 3x squared minus sine of x, then we could say, oh, it looks like the top is exactly the derivative of the bottom. It is. And so our antiderivative is going to be capital G of x equal to the natural log of the bottom plus c. And we can check, if we take the derivative of this, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the inside, which is 3x squared plus negative sine of x. And that exactly works out to be the same as the thing we started with. So that's what we're doing there. We're seeing that if we have a derivative of something over that something, the antiderivative of that quotient is the natural log of the denominator. And then I'll just point out, although I don't think we need to get too into detail here, problem 5 was kind of worded in a way on this discussion sheet to make you have to kind of think, I suppose, weirdly. So here's what the words say. Find a function f of x whose antiderivative is given as y equal to capital F of x. And then, for example, they gave you something like y equals x cubed times e to the x. Okay, this question's worded weirdly, but if you read it carefully, what they're asking you to do is find the derivative of the thing that you're given, right? They're saying, great, here's the antiderivative, find the thing that it's the antiderivative of. Oh, that thing has to be the derivative of that. So if we want to find f of x, right, if this is our capital F, our little f of x is just dy dx or y prime. And then we take the derivative using whatever rules. Here we're using the product rule and getting 3x squared times leave e to the x alone, plus x cubed left alone times the derivative of e to the x, which is e to the x. But the question feels like it's worded in a very kind of circuitous way where you're like, what are they really asking me to do here? Or they're really asking me to just take the derivative, but they're phrasing it as find the function whose antiderivative is the thing that's given, which seems a little bit weird, but I understand why you might ask it that way. All right, I think that's all I wanted to talk about as far as that discussion sheet. I think his discussion sheets are good. Again, the solutions are provided there as well, so I encourage you to look at them if you have questions about it. Not that I'm not happy to talk about it in class, just there's also that resource that provided to you. For those of you that are not in the adults class, I feel like it might be worth actually posting his discussion sheets and the solutions in our Canvas just so you can see them, because it's always good to have more resources. So I'll try to remind myself to do that. Yeah, let me write that. Let me write myself a note here. Post discussion sheet. That's a good idea. You obviously do not have to look at them, but again, it's just another useful resource for those of you not in his class. Let's go ahead and talk about some properties of integrals. Yeah, so area under a curve and definite. So let's start off with something that's not terrible. Well, it seems like it's not terrible, but actually seems like it is terrible. Sorry. Let's say I want to find the integral or the area under the curve from 0 to 4 of the square root of 16 minus x squared. So the point of a question like this is that we have to remind ourselves that this question is really just asking us to find the area under the curve. And they're not specifying how we have to do this. You can use whatever area knowledge you have, meaning if we know what this function looks like, y equal to the square root of 16 minus x squared, which you may not recognize immediately, but if you square both sides and then bring the x squared over to the left, you might recognize that x squared plus y squared equal to 16 is the equation of what kind of shape? The circle. So y equal to the square root of 16 minus x squared is the top half of that circle. So this function here really looks like the top half of a circle centered at the origin, whose radius happens to be the square root of 16, which is 4. So this point here is 4, 0. This point here is 0, 4. This point here is -4, 0. But it is only the top half, because if y is equal to the square root of 16 minus x squared, y has to be positive. It can't be negative. So then, if we're trying to find the area under this curve, as far left as x equals 0, as far right as x equals 4, I'm looking at shading in this region here, which is just a quarter of a circle. So this area is equal to 1/4 of pi times my radius, which is 4, squared, which happens to simplify to 4 pi. And it's perfectly valid to find the area under a curve using geometric formulas that you're aware of. Let me show you another example that comes up frequently where the expectation is you do it this sort of way. I should also point out, this is kind of the only way that we are going to talk about how you find the area under a curve like this. There is a way of anti-differentiating this and using the fundamental theorem of calculus that we do not learn in this class. So when you see something like square root of 16 minus x squared all by itself, you think, oh, that looks like part of a circle. And just do it that way. Here's another area kind of question that comes up.
Excuse me?
Yeah, go ahead.
How did you know that it was a semi or like a quarter of a circle?
Right. So why wasn't it like the whole entire top half? Well, because these limits of integration tell you that your left-hand value starts at x equal to 0. So we're starting right here at x equal to 0. And then we're ending over here at our right-hand limit, which is going to be x equal to 4, which ends right there. So that's kind of how we know that we're only getting the quarter. On the other hand, if the question had been the integral from -4 to 4 of the square root of 16 minus x squared, then it would have been equal to 1/2 the area of a circle, which is pi, times the radius squared, which would have been 8 pi. That clarify what's going on there?
Yeah, thank you.
You're welcome. Another area thing that comes up is something like the integral from -1 to 5 of the absolute value of 2x minus 7. I will point out, you can do this using the fundamental theorem of calculus if you break apart the absolute value function into 2 different pieces. But that's not the easiest way to do it. The easiest way to do it is to first graph this function here. So I'm going to graph the absolute value of 2x minus 7. And when I'm graphing this, the things I think about are, I know it's a V shape, and I want to find the bottom of the V. To find the bottom of the V, I'm going to set the insides of the absolute value equal to 0. So I get 2x equal to 7. I get x equal to 7/2 or 3.5. So when I graph this, I'm also going to see what happens at the leftmost and the rightmost endpoint. If I plug in -1, 2 times, let's just plug it in. If I have f of x equal to the absolute value of 2x minus 7, then f of -1 is going to be the absolute value of -2 minus 7, which is the absolute value of -9. When I plug in 5, f of 5 is going to be the absolute value of 2 times 5 minus 7, which is 10 minus 7, so 3. So over here, when I plug in -1, I get 9. When I plug in 5, I get 3. And then I know that the bottom of the V is over here, like it's 7/2, which is like there-ish. So it looks something like this. If I'm trying to find the area under this curve that continues on that way, I'm just trying to find some areas of triangles. And that's not terrible at all. That first triangle, the area is going to be 1/2 the base times the height, which is 1/2. Let's see, the base is 3.5 plus 1. The height was 9. Sorry, I didn't label that. I really don't love decimals. I would much rather write this as 1/2 times 9/2 times 9, which ends up being 9 times 9 over 2 times 2. And then for the other triangle, same sort of thing. The area of that other triangle is going to be 1/2 the base. The base is 5 minus 3.5 times the height, which is 3. Again, I don't love decimals. That's 1/2 times 3/2 times 3, which ends up being 3 times 3 over 2 times 2. And then we'd add these together to get a total area of 81/4 plus 9/4, which is 90/4, which reduces to 45/2. Or if you like a decimal, 22.5. So the point of this kind of problem is that you don't have to do it using a different method. You could do this a different way, but often if we can see that the region is just going to be a triangle shape, we find its area by observing that it's a triangle and using the formula for the area of a triangle. But that's not always going to be the case. There's plenty of functions whose areas are curvaceous and don't lend themselves to just using a geometric formula. So when that comes to be what we see, we then have to appeal to something else. And I guess, yeah, this is probably the time. So let's talk about the fundamental theorem of calculus. And really, let's just start off with an example when we'll come back around to the fundamental theorem. So let's say we wanted to find the area under f of x equal to 3x squared plus 4x plus 5 on the interval from 1 to 3. First of all, here's how we would write it. We would express this as the integral from 1 to 3 of 3x squared plus 4x plus 5. And the fundamental theorem of calculus, which again, I know we haven't written down yet, but here's what the fundamental theorem of calculus tells us we can do. To find this area, instead of using the limit definition, which we totally could do here, right? We could write this as the limit of the sum of something terrible and then multiply it all out and use those formulas. We don't want to do all that. Instead, we're going to say, well, alternatively, the way we can evaluate this is by finding the antiderivative of this function. The antiderivative of 3x squared plus 4x plus 5 is going to be 3x cubed over 3 plus 4x squared over 2 plus 5x. We don't need a plus c here, although it would be totally fine if you did write one. So they end up canceling each other out. And then we're going to evaluate that between our limits of integration from 1 to 3. That's essentially there. So that's half of the fundamental theorem of calculus, what this part says here. This is the second part of the fundamental theorem of calculus, which is the part you're going to use more. And then we can simplify if you want to. And say this is x cubed plus 2x squared plus 5x, evaluated from 1 to 3. And then you plug in the top value first. So you get 3 cubed plus 2 times 3 squared plus 5 times 3. And we subtract and plug in the bottom value second. 1 cubed plus 2 times 1 squared plus 5 times 1. And then simplifying this, we have 27 plus 2 times 9 plus 15 minus 1 plus 2 plus 5. That's going to be, let's see, 45 plus 15 is 60 minus 8, so 52. So the area under that curve is 52. 52, whatever, square inches, square feet, whatever you're measuring. And although really we just don't even talk about units. We just say 52. So that's what I would say you're going to do most of your fundamental theorem of calculus work with. But there is more to it. So let's kind of talk about the bigger picture here. So fundamental theorem of calculus says two things. The first part says that the derivative of the integral is the function you started with, which is something we've been saying all the time so far, right? If you do the antiderivative of something and take the derivative of that, you end up back where you started. So really, that's what I would like you to hear when you see this is the derivative of the antiderivative of a function is just the function. Here's how we actually write it mathematically. We're going to write this as the derivative with respect to x of the integral from a to x, where a is a constant, of some function. Now, here's where things are a little bit weird. We're going to write f of t, not f of x, because we've already kind of used the x. So we're going to say f of t dt is equal to f of x. That's the whole story. The derivative of the antiderivative of the function f is the function f. Let's look at an example. Let's say I want to find the derivative of the antiderivative from 1 to 4 of, sure, what have I got here? Let me think for a second. 4, is that really? Yeah, sure, why not? Of t cubed dt. Sorry, I made a mistake. It's not a big deal. We can fix it. I don't want to stop at 4. I want to stop at x. I'm like, so let me just point out. If we did this, our answer would end up being 0. Because the integral from 1 to 4 of t cubed dt is just the area under the curve. And the area under the curve, whatever that number that ends up being, is a constant. Would never change. This would be, I don't know, 64, I don't know. It'd be something. I don't actually care what it is. But then if you take the derivative of that constant, it would be 0. But I don't want a 4 there. I really want an x there. So let's find what's happening in this bracket here. So I'm going to find the derivative of, well, the antiderivative of t cubed is t to the 4th over 4, evaluated from 1 to x. We plug in the x first and the 1 second. That's going to be the derivative of x to the 4th over 4 minus 1 to the 4th over 4. But then the derivative of x to the 4th over 4 is exactly 4x cubed over 4. And the derivative of 1 to the 4th over 4, well, 1 to the 4th is just 1, and 1 over 4 is just a constant. The derivative of a constant is just 0. So we end up exactly where we started, and the only difference is we've changed the name of the variable from t to x. Question?
Do we have to show all of the
No, that's exactly the point of the fundamental theorem of calculus is you don't have to show this work, and sometimes you can't show this work. So for example, one paper here. Right, the whole point is that there are many functions where you can't do all that. So for example, if I said, what's the derivative of the antiderivative from 2 to x of, let's say, something terrible like t, sorry, it has to be a t to the fourth e to the t squared, it might be true. It's probably not true, but it might be true that you could find the antiderivative of t to the fourth e to the t squared. My guess would be that we probably can't, or if we can, it's going to be really terrible. But again, that's not the point. The point is that we know that the derivative of the antiderivative of some function is just the same function, except we replace the t's with x's. That's it. And so, no, whenever someone asks you something like this, unless they specify that they want you to kind of do it the long way, we are always intended to do it the shorter way. We're just like, oh yeah, the fundamental theorem of calculus says the derivative of the antiderivative is just the function you started with. Now, there is a slightly more complicated version of this first part of the fundamental theorem of calculus, where if your x up here is something other than just x on its own, we have to work a little bit harder. So let's say, and we'll do this by example as well. Let's say we wanted to find the derivative of the integral from -4 to x cubed of something that we can do not too terribly. Let's say cosine of t dt. And someone asked, how did I get 4x to the 7th? That might be a 3, not a 7 that you saw. Sorry, is that if you're referring to this part right here, that's a 4x cubed, not a 4x to the 7th. Hopefully that's what you were asking about. I don't see where else that would have been. Yeah, sorry about that. So we could, so if I, well, no, let's do this one the long way. So the antiderivative cosine of t is, oh, what is it? Is it sine or is it negative sine? So yeah, so here's a good thing that I've written down a few times that I think people might appreciate. If you start with sine of x, what's the derivative of sine of x? Cosine. What's the derivative of cosine? What's the derivative of negative sine? What's the derivative of negative cosine? Back to where we started. And if you go down this way, those are derivatives. But if you go up the opposite way, those are antiderivatives. So the antiderivative of sine is negative cosine, and the antiderivative of cosine is positive sine. I think it's somewhat useful. So here, the antiderivative of cosine is positive sine, so we're going to get the derivative of sine of t evaluated between -4 and positive x cubed. Plug in your limits of integration, you get the derivative of sine of x cubed minus sine of -4. And now we're going to take the derivative of that. The derivative of sine of x is cosine of x. The derivative of sine of some stuff is going to be cosine of that stuff. And then the chain rule says we have to multiply by the derivative of the inside stuff. And I don't know what sine of -4 is, but I know it's a constant. I know it's something that never changes. There's no variable there. It's not a nice number, but it is a constant. And the derivative of a constant is going to be 0. So the derivative of sine of -4 is just 0, whatever that happens to be. So look what we got. We didn't just get cosine of x cubed. We got cosine of x cubed times the derivative of x cubed. So more generally, what happens is when this function up here, or when this thing that with x in it is more complicated than just x, when it's a function of x, you end up plugging that in for every t, and then at the end of the day, multiplying by the derivative of that. So another example, if I wanted to find the derivative of the integral from 2 to x to the 5th of t squared over sine of t plus t to the 3rd, which seems terrible. All I'm going to end up doing is wherever I see a t, I'm going to plug in x to the 5th. So I'm going to write x to the 5th squared over sine of x to the 5th plus x to the, that is a 5, I promise you, plus x to the 5th cubed And now that I plugged in x to the fifth for every t, what do I have to multiply by? X to the fourth, the derivative of x to the fifth. So this is the chain rule version of the fundamental theory of calculus part 1. So fundamental theory of calculus part 1 says that the derivative of the integral from some constant to some function of x of f of t dt is equal to f of g of x times g prime of x. Or if you
I have a question.
Oh, 1 second. 1 sec. I promise you. I'll just point out, or if you want to think of this as, say, capital F of g of x, you're getting the derivative is going to be capital F prime of g of x times g prime of x, which might look a little bit more like the chain rule you're used to seeing. The derivative of the outer function, leave the insides alone, multiply by the derivative of the inside. Question on Zoom here. Was there a
I was
question?
gonna ask, why did you subtract by negative sign? Yeah, on the other example above it, why did you subtract by negative sign of 4, I think it was?
Sign of -4 right here. Is that what you're asking about? Why I'm subtracting this?
Yes.
So the reason I'm subtracting that is because when we do the antiderivative of something for a definite integral with endpoints like this, we always plug in the top value first, x cubed, and then we subtract and plug in the bottom value second. And so again, we wouldn't normally show all this work if we're trying to take the derivative here. We would just jump to the end and say, oh, we're going to plug in the x cubed and multiply by the derivative of x cubed, which is 3x squared. The reason we're plugging this in here is to show that no matter what that happens to be, when you take the derivative of this constant, and this is a constant, plug it into your calculator, see what sine of -4 is. It's something that never changes. Its derivative is going to be 0. Yeah.
Is that why? You guys do anything, the x.
Exactly. That's exactly why right here, the 2 is not important at all. If I found the antiderivative of this, it would be something terrible. And then I would plug in the 2, and whatever it happened to be, that would be a constant. And then its derivative would be 0. That's why the constant part doesn't ever matter, as if you're doing this derivative of the antiderivative here. Yeah. So let me ask you a different question. So here, why did I multiply by 3x squared? Right, because I'm taking the derivative of sine of x cubed. So the idea here really is that, so let's say, so right here, actually, let's say, yeah, sure. So what's happening here is, I don't know what the antiderivative of f of t is, but let's pretend like we did. So we're going to say, okay, the antiderivative from a to g of x of little f of t, we're going to say that the antiderivative of little f of t is capital F of t, evaluated between the constant a and the function g of x. Note, we are saying that the derivative of capital F of t is equal to little f of t, which is another way of saying that capital F is the antiderivative of little f. Then I'm going to plug in. I'm going to get capital F of g of x minus capital F of a. This part here is a function of x. This part here is a constant, right? If you take a function and plug in a number, you get out some numerical value. You don't get out something variable. This is a number, a constant. And we then take the derivative of all this, the derivative of the integral from a to g of x of f of t dt is equal to the derivative of capital F of g of x minus capital F of a. The derivative of f of g of x, well, that's where the chain rule is going to come into play. It's going to be the derivative of the outer function. We'll leave the insides alone, but then I have to multiply by, right, the derivative of the inside. over here, and then the derivative of f of a, well, again, f of a is a constant, its derivative is 0. But then capital F prime is really the same as little f. So I'm going to rewrite this as little f of g of x times g prime of x. So to answer your question in kind of a very long way, over here, that's exactly what I was doing. I was saying, okay, this function, this is my f of t, and now over here I'm getting f of x to the 5th, but then I have to multiply by the derivative of the g of x function there, which is x to the 5th. So this is the derivative of my x to the 5th. That's what's happening there. All right, let's see how you all feel about that. I want you all to try to find the derivative of the antiderivative from 4 to x to the 4th of, sure, secant of t cosine, cosine is the worst thing I could have written there. Let's change that to cotangent of t dt. Find that derivative. It should be a very fast process. Okay. No work needs to be shown. Hopefully we're getting secant of x to the 4th times cotangent of x to the 4th times 4x cubed. End of story. Nothing else left to say there. What would happen if we were asked to find the derivative of the antiderivative from x cubed plus x to 5 of cosine of t plus t cubed dt? My stuff's in the bottom now. What's that going to do for me? Well, one way of fixing this is using one of the properties of integrals, of definite integrals, which says if you have limits of integration, you can change the order of limits of integration if you change the sign of the integral. So we could definitely rewrite this as the derivative of the negative of the antiderivative from 5 to x cubed plus x times cosine of t plus t cubed dt. Then the negative is just going to hang out, and we do the usual thing. We plug in x cubed plus x for each t, so we're going to get cosine of x cubed plus x plus x cubed. All of that has to get multiplied by the derivative of x cubed plus x, which is 3x squared plus 1. And then what I'll point out is that usually we just skip this step here and just say, oh, great. We know that if the things in the bottom instead of in the top, we just get the negative of what we would have gotten, because we could just do the work of switching it, but we don't show it. Why didn't we take the derivative for secant and cotangent in the first example? So we didn't take the derivative of secant and cotangent because we're not taking the derivative of secant and cotangent. We're taking the derivative of the antiderivative of secant times cotangent. Just like here, right? The same sort of reason, not here, that's not great. It's like here, right? The same reason we didn't end up taking the derivative of cosine, right? We just ended up with cosine of x cubed times 3x squared, because there was an antiderivative that we took the derivative of to get where we wanted to be. Okay, let's talk about the rest of the fundamental theorem. So this part of the fundamental theorem of calculus, where you take the derivative of the antiderivative, we use a little bit, but it's certainly the more kind of important conceptual thing, in that it's really, really important that we understand that the derivative and the antiderivative undo each other. If you do the antiderivative and the derivative, you end up back where you started. But the more practical piece of the fundamental theorem of calculus is the second piece of it. So here's the fundamental theorem of calculus in its entirety. The fundamental theorem of calculus, part 1. Let's write it again real quick. The derivative of the antiderivative from a, I'm going to write the general version, from a to g of x of f of t dt is equal to f of g of x times g prime of x. I'll point out that if g of x was equal to x, you would just get you'd get f of x times 1 because the derivative of x is 1, so it works out like we think it would. And then the second part is that the definite integral from a to b of f of x dx is going to be equal to, I don't prefer to write it this way, but I will, capital F of b minus capital F of a. I find the nicer way to write this to be as capital F of x evaluated from a to b, where capital F of x is an antiderivative of little f of x. Or otherwise phrased, the derivative of capital F is equal to little f. So this is how we're actually going to find the area under a curve. We're going to say, oh, instead of trying to use this limit definition of the integral, we're going to anti-differentiate the function and then plug in your limits of integration to find the area. And this is why we use this notation to mean the antiderivative, because there's this natural association between finding the integral of a function, finding the area under the curve, and finding the antiderivative, because we're using the antiderivative to find the area. So I'll point out a definite integral has limits of integration. It looks something very generally like this: the integral from a to b of f of x dx. An example of that could be the integral from -1 to 4 of 2x squared plus 5x. And your answer to a definite integral is going to be a number. Some amount of, I should really say, it's not just the area of the curve, it's actually the net area that's under the curve that's above the x-axis. Whereas an indefinite integral does not have limits of integration. It is something like the antiderivative of f of x dx. And it looks something like just the antiderivative of 2x squared plus 5x. And here our answer is going to be just, and if you need to go, you're welcome to go. Always, it's not a problem, you can take off. But here, for this indefinite integral, our answer is just going to be the antiderivative. 2x cubed over 3 plus 5x squared over 2 plus c. Here, I don't want to write that because I don't have enough room, but here you would get some numerical answer. It's probably terrible. So, indefinite integrals, your answer is a function. Definite integrals, your answer is a value. Yeah.
So I guess like the main question is like in homework, if it was like, oh, like find the general like indefinite integral, that's when we would get the equation. But if it was like, oh, find the general definite integral, then we get an.
Right, and I wouldn't say I wouldn't say, usually when you're talking about definite integrals, the word general is not associated with that.
Okay.
If you're finding a definite integral, you're always given a specific interval of integration.
Okay.
So, for example, we could be asked to find the integral from -1 to 3 of 4x squared plus 2x plus 7. And there's a lot of things we are doing when we integrate that are using properties of integration that we don't even realize. Like, for example, when we integrate this or anti-differentiate this, we're just going to anti-differentiate each piece and then add all the results together, like we've been doing. But it definitely is a rule or a property of integrals that I think Dr. Didell mentioned, which is like if you have the integral of f of x plus or minus g of x, it's the integral of f of x plus or minus the integral of g of x. We never really think about using that rule. It is certainly a rule you can use, and sometimes it is convenient to break up an integral into multiple integrals. But most of the time, we're just like, okay, yeah, let's find the antiderivative. That's going to be 4x cubed over 3 plus 2x squared over 2 plus 7x. I don't need a plus c here because it's a definite integral. evaluated from -1 to +3. I do encourage you to say from the bottom to the top. That's how we usually read definite integrals, from the lower limit of integration to the upper limit of integration. And then we're going to plug in the top one first and subtract and plug in the bottom second. So I'm going to get 4 times 3 cubed over 3 plus 2 times 3. I could have canceled the 2's there. Oh, well. Plus 7 times 3 minus 4 times -1 cubed over 3 plus, let's just cancel the 2's and say we have -1 squared plus 7 times -1. For the most part, I'm not trying to simplify this unless I have to. Sometimes you have to, but most of the time, I would leave this like this. If I was doing a web work problem, I would probably, typing this into web work would probably be terrible. I'd probably do some simplification here. So I would point out that 3 cubed over 3, you can cancel a 3 and get 4 times 3 squared plus the 2's cancel, you get another 3 squared. 7 times 3 is 21 minus, okay, you're stuck here with a -4/3 plus 1 minus 7. And so then I might have, let's see, 4 times 9 is 36. 9 plus 21 is 30. I would probably distribute the minus sign and get plus 4/3. 1 minus 7 is -6, minus -6 is +6. So I might stop at writing this as 36 plus 36 is 72 plus 4/3, or maybe 73 plus 1/3. Or you could get an improper fraction if you really wanted to, right? As, I don't know, some number over 3, 200 and something over 3. But this is our answer, and it is a numerical value. How much time? We got 5 whole minutes. So let's see here. I was hoping to talk about the properties of integrals. I don't think we're gonna have time. So let me talk about one property of integrals I do think comes up quite often. Let's say we're given the following. Wrote something down here. Let's see where did I put you. There you go. Yeah. No, sorry. There we go, right there. So let's see. So let's say we are given that the integral from 1 to 7 of some function is equal to 23. We're also given that the integral from 5 to 7 of that same function is equal to 6. And we're then asked, what is the integral from 1 to 5 of f of x dx? Sometimes it's easy to see this, sometimes it's not. If we draw a picture, it's a little more clear. So I've got some function, I don't really know what it looks like. And I'm going from 1 to 7. And I've been told that the area under the curve between x equals 5 and x equals 7, so let's put a 5 down there. I've been told that this area is 6. And I've been told that the total area under the curve is 23. So all of this in green, that's 23. So this leftover part here, or the difference here in black, well, I already said it, that has to be the difference. So this black part has to be 23 minus 6, which is what, 17? Because this area here is 17, plus this area here is 6, has to add it to that area there, 23. Another way of writing this is that we could have said that the area under the curve from 1 to 5 plus the area under the curve from 5 to 7 has to equal the area under the curve from 1 to 7. Right? If you go from 1 to 5 and then 5 to 7, that's the same as going from 1 to 7. We know that the area under the curve from 5 to 7 is 6. We know that's 23. So this has to be the difference, 17. What I think is more interesting about this, maybe not more interesting, but certainly interesting, is that you can write this as a more general formula that, so here's one of the properties of integrals. One of these properties, which hopefully you can see what I'm writing here. Yep, cool. Is that the integral from a to b of f of x dx can always be broken up at any c. So you can go from A to C of f of x dx plus C to B of f of x dx. And B can actually be anywhere. It doesn't have to be between A and C, which is kind of neat. Yeah.
If this were to be on an exam,
Mhm.
do you think he wants us to like show our work, like through the graph?
Good question. Yeah, I mean, I would, if I was trying to show my work and not do a whole lot of work, I would probably write down this. I think that is the easiest way to express what I'm doing. Yeah. But yeah, so this idea here, that the integral from A to B of f of x can be broken up at any point C makes sense if you're thinking about C being somewhere in the middle, right? You've got like this region here, there's the area from A to C. And here's the area end of the curve from C to B. But it also works if C isn't in between them. So, yeah. Sorry, I'm like, I have a minute. I'm trying to see, like, do I really have enough time to say this? No, not really. So next time we talk about, if you want, why C can actually be, so I'll point out here that C does not have to be between A and B. And I guess I'll leave you with a cliffhanger.